Hi, I hope I find you well again. My name is Farai and welcome to the channel Magetsi 2.0, a channel that is all about everything electrical. In the previous video, we defined electricity, electrical energy, and power in an electric circuit. We also established the equations for power and energy in an electric circuit, which link both voltage and current. Now, these equations can be used to calculate power and energy in both AC and DC circuits. If you haven't watched that video, please do so. Please note, when we define current or voltage to specify whether it's direct or alternating, we define using current. Hence the reason why we talk about DC voltage or AC voltage. Normally, we do this when there is a need to specify whether it's DC or AC. So now, as we proceed with our definition of electricity, it is important that we go over some common DC and AC energy sources. Let's start with DC. There are many DC energy sources, but for simplicity, we'll dwell on the most common ones. So on DC, we have batteries, rectifiers, solar panels, and for alternating current or AC, we have main supply, diesel or petrol engine generators, or inverters. Now, let's dive into some examples featuring DC and AC power sources. We'll start with DC. Let's say we have a 12-volt car battery. If it's not connected to any external circuit or load, there is no flow of charge, so there is no current flowing. If it's a charged and rested battery and we measure between its terminals, we'll get a typical voltage of around 12.6 volts. Now let's see what happens if we connect a 12-volt DC 60-watt light bulb to the battery. One thing to note is that a battery will exhibit a drop in voltage if a load is connected to it, but for simplicity, we'll do our calculations at the nominal voltage, which is 12 volts. Now for this light bulb, ignoring all system losses in the light bulb circuit, the method for calculating the current through the light bulb is as follows. Now, since power is equals to voltage times current, or P is equals to V times I, which is equals to 60 watts, this value we've already been given. So to calculate current, we make I the subject of the formula. Hence, current I is equals to P over V equals to power over voltage, which is 60 divided by 12, which gives us 5 amps. That's the current that flows through the light bulb. Now, for us to be able to calculate the energy consumed by the light bulb or the energy discharged by the battery to power the light bulb, we need to have another variable, which is time. Now, let's imagine that this light bulb stayed on for 6 hours. So how we calculate the energy consumed by the light bulb is as follows. We know that energy is equals to power times time, and our power is 60 watts, our time is 6 hours. So 60 by 6 is 360 watt hours. So 360 watt hours is the energy consumed by the light bulb. If we ignore system losses, it is also the same energy discharged by the battery. Hence, energy consumed by the bulb is equals to energy discharged by the battery, which is 360 watt hours. Now, let's look at another example involving an AC power source and load. Let's imagine that we have a 1000 watt toaster that is plugged onto an AC supply and stays on for, say, 6 minutes. So in order to calculate the energy consumed by this toaster. We know that in our calculations for energy, we are referring to our time in terms of hours. But if this toaster is plugged onto an AC source for 6 minutes and we want to calculate the energy consumed for that 6-minute period, then we have to convert that 6 minutes to hours. And how we do this is by taking 6 minutes as a fraction of 60 minutes, which is 1 hour. So we say 6 minutes is equals to 6 divided by 60 equals to 0.1 hours. So energy consumed by the toaster over the 6-minute period is equals to power times time equals to 1000 watts times 0.1 hours equals to 100 watt hours. Now, let's look at one last example and let's spice it up a little bit by mixing AC and DC into this scenario. Let's imagine that we have a 1500 watt inverter which is 12 volt on the DC side, and we connect that 1500 watt inverter to the car battery that we mentioned before. On the AC output of that inverter, let's just say that inverter is giving out 220 volts AC. On that 220 volt AC output, we are connecting a 250 watt infrared light. Now we know that an inverter converts DC power to AC power that is usable by most of our everyday appliances inside the home or in our workplaces. So when that happens, when an inverter converts DC to AC, there are losses. Like on this kind of system, we are converting 12 volts DC, we convert it to AC and then step it up to the voltage that we need, which is 220 volts. In that process, there are some losses that occur depending on the architecture of the inverter. Sometimes an inverter could be 70% or 80% efficient. So which means that for every 70 or 80 watts that we require to power our load, we are going to be drawing 100 watts from the battery. But for this particular example, let's imagine a perfect system with no losses. So what we are discharging from the battery is exactly what we are using to power our load. So that's how we're going to go about this one. So, I don't want people coming and saying, there's no system without losses. We know. But for simplicity, let's imagine this one doesn't have any losses. For this example, we have a 1500 watt inverter that is connected to a 12 volt car battery, the battery that we've been talking about all the time. So, and then to that 1500 watt inverter, we are connecting a 250 watt infrared light. Now, for the sake of simplicity and for our calculations here, we've imagined a perfect system with no losses. Hence, power input is equals to power output, which is 250 watts on both the DC and the AC side. Now, let's calculate current on both the DC and AC sides and examine its behavior. To calculate the current discharged from the battery, we use the equation power is equals to voltage times time. Hence, to calculate current, we just make current the subject of the formula. So current I is equals to power divided by voltage, which is 250 divided by 12, which gives us 20.83 amps. That is the DC current from the battery at 12 volts. Then the current drawn by the load is calculated in the same way as well. And since our load is a 250 watt infrared light, then our current is calculated by the same method basically, which is current is equals to power divided by voltage, which is 250 watts divided by 220 volts, which gives us 1.14 amps. Now, do you notice the relationship between power, voltage, and current? For the same value of power, if voltage increases, current decreases and vice versa. This is what's happening. Now, let's imagine this infrared light runs for 2 hours. If we know the amount of time that it runs, then we are able to calculate the energy that the infrared light is drawing from our system. So we can calculate it as follows. Energy is equals to power times time, which is 250 watts times 2 hours, and gives us 500 watt hours. Now, assuming a perfect system with no conversion losses, energy discharged from the battery is the same as the energy consumed, which is 500 watt hours. We can also express energy consumed or discharged in terms of kilowatt hours by dividing by 1,000. So 500 watt hours is the same as 0.5 kilowatt hours. That is the energy consumed by this infrared light over a 2-hour period. It is also the energy supplied by the battery to power this load over that 2-hour period. Now, that's it, people. The goal here was to get a better understanding about electrical energy and power by exploring DC and AC examples. And I hope that you'll be able to at least perform some simple calculations involving power and energy in DC and AC electrical systems. Now, if you didn't quite get it, I would advise that you go over this video or the previous one so that you get a better understanding of what we are really talking about. And you realize that as we progress, these topics will make certain practical issues that we're going to tackle much easier to understand. So that's why we are going through the trouble of covering all these basics, so that it's easier to cover the practical aspects that we intend to cover on this channel. So please like and subscribe to this channel. Join us on the next video. Ndatenda.
Isai mawoko toda kutenda misha. Isai mawoko woye. Isai mawoko toda kutenda misha. Misha woye. Misha woye. Misha we Magetsi. Misha we Magetsi. Misha woye. Misha woye. Misha we Magetsi. Misha we Magetsi.